All right, in this video, I'm going to quickly review the valence electrons from the periodic table and then go over how to determine the geometry of our Lewis structure examples. All right, so in this periodic table, you can typically just number the top 1, 2, skip the transition metals, 3, 4, 5, 6, 7, 8. And now you have your groups, and that tells you the number of valence electrons for each substance or atom in that group. All right, from the previous video, I have pulled over much nicer drawings of the Lewis structures so that we can use those. And there is also a table just like this one that you can find in your notes, and I'm going to show you how to use it. All right, so you're going to look at the number of domains. The number of domains is how many things are on the central atom. So let's look at our carbonate ion. Around the central atom of carbon, we have 1, 2, 3 domains. All right, so that means we're going to go to the row that has 3 domains in our table. The electronic geometry is trigonal planar, and I have 0 lone pairs. So the lone pairs are listed here. I have 0 lone pairs, and therefore the molecular geometry is also called trigonal planar. When you have 0 lone pairs, the electronic and molecular geometries are the same. So we have trigonal planar. Trigonal planar. All right, so let's move on to the nitrogen trifluoride. Around the nitrogen, which is the central atom, we have 1, 2, 3, 4 domains and 1 lone pair. So 4 total domains where one of them is a lone pair on the central atom. So now we are going to go to our table and go to 4 domains. The electronic geometry is tetrahedral. This is how 4 groups arrange themselves around a central atom. And within that arrangement, if one of them is a lone pair, I'm going to jump over here. 1 lone pair is going to give me a trigonal pyramidal geometry, trigonal pyramid. So it's a tetrahedral electronic geometry because it has 4 domains, and one of those domains is a lone pair, so the molecular geometry is trigonal pyramid. All right, so now you can do a similar analysis. I would pause the video and see if you could determine the geometry of the other 2 molecules. All right, hopefully you were able to figure out how to do this. Over here, I am still going to use carbon as the central atom. Sometimes the question will identify which atom you need to look at for a central atom if there's more than one. But this carbon has 1, 2, 3 groups. Notice that double bonds count as a single group. It's bonded atoms and lone pairs around the central atom. So this is 1 bonded oxygen to that carbon. So I still have 3 groups, so it's the same as the carbonate was before, trigonal planar and trigonal planar. We have 3 domains and 0 lone pairs. All right, let's go to astatine. All right, this is the one that earlier I told you it breaks the octet rule. So let's go over a little bit about why it can break the octet rule. If you return to the periodic table and you remember a little bit of something about electron configurations with S, 1s2, 2s2, 2p6, 3s2, that kind of thing. Don't worry, you don't have to do that. But the 3, the third row, has the third row and below always has an empty D shell that can hold a few more electrons. So here we're using 3s and 3p, but a 3d orbital or subshell also exists, and it's empty for these atoms if they're a central atom, and it can sort of hold extra electrons. So that is why we are able to break the octet rule. You cannot break the octet rule for row 2 or row 1 because there is no 2D subshell. But row 3 and further below you can. All right. So for astatine, we have 5 groups here. 1, 2, 3, 4, 5. All right, so let's go back to our handout. And we are going to go to 5 groups. When you have 5 domains, it's called trigonal bipyramidal. So you're in the trigonal bipyramidal family. And I'm going to have to abbreviate here. That's the electronic geometry. And we have 0 lone pairs. So with 0 lone pairs, the molecular geometry has the same name. So that's quickly how to use the table. For more important information going into the next unit, you're going to need to understand the polarity of each geometry. And there is a set of videos that goes through each family and how to interpret the geometry. And I encourage you to watch those.